Our next speaker is Dr. Shaun Molloy. Shaun is a postdoctoral research fellow with the Centre for Ecosystem Management. He's currently engaged to work on spatial modelling applications for the conservation of the Pilbara population of the northern Quoll. Shaun has recently been awarded a PhD by Edith Cowan University for his work on spatial modelling of fauna, with a focus on how to model species movements in different landscapes, the impacts of climate change on species distributions and animal ecology. Among his other qualifications, Shaun holds a Master's in Wildlife Management from Macquarie University. Thanks, Shaun.
Okay. I'd like to thank Pandora and Keith because they've pretty much set me up for this. They've discussed the problems that are really out there. What I'm looking at is, what they've set up is a situation that's going to require severe management actions, and what we're talking about is undertaking modelling that will inform those management actions. And one of the most important parts of these is species distribution modelling. Okay, what is a species distribution model? These are statistical and GIS-based software models that compare observations of species occurrence and abundance with habitat variable data sets. Basically, it's looking at where they are and those factors, those variables that help define where they are. Could be something like topography, climate, soils, that sort of data set you combine to where you can identify potential distributions. That is where species and communities might be persisting. Given appropriate variable data, SDMs can be used to demonstrate how distributions can change over space and time. If we've got a bioclimatically defined distribution, if we can use a climate model to see how those bioclimatic variables are going to change, we can see how the distribution of an animal is going to change over time. And the purpose of the SDM is to facilitate the development of management actions by informing expert opinion, not replacing it and not substituting it, which is a mistake a lot of people make with their modelling. Something I've got to fess up. I've been working with these things for 5 years and I'm still not sure how valuable they are. They can be really good things, but there's a lot of really bad ones out there because there are problems associated with them that need to be addressed and most often are not addressed, and they include species suitability. Not all species are amenable to distribution modelling, not to the same degree. Sample bias. Do you have enough presence data out there? Do you know enough about where they are to be able to predict where they're going to be in the future? And are people compensating for that bias? Inappropriate variables. Are you using the right predictive variables? Testing. Are you actually testing your models? Are you modelling at the right scale or resolution? Are you using too many variables? If you've got too many variables, your model can look statistically much better than it is, but you're getting noise. It's not going to reflect change. It becomes a dishonest model, so to speak. And are you using the appropriate modelling tool? There are a lot of tools out there. They have different strengths and weaknesses, and they have different suitabilities. People tend to use simple and easy modelling tools for all purposes. So my first modelling project, this was the new year, the Western ringtail possum. It's already down to about 1/5 of its original distribution, and it's highly susceptible to the impacts of climate change. In this model, this is my first attempt at species distribution modelling. We're using bioclimatic data alone, and we wanted to see how climate change might be affecting this species. I used 3 different modelling tools, Maxent, Domain and Support Vector Machine, developed different suites of predictive variables for each modelling tool, combined them all, and we ran those different modelling tools past different climate scenarios. And if you look at that, first one's baseline. After that, we have combinations of 3 different models, 3 different global climate models. You can see there's a lot of variation between them. They're all telling different things. So how do you make sense out of it? In this case, we put it together and we generalised roughly to see what is the most likely scenario out of all those. We combine those with models for the tree species on which they're the most dependent, jarrah, marri and peppermint. Put that all together along with future data on vesting, conservation, estate and forestry. And we found through that basically the extent of this species is probably going to decline about another 60%. It's going to move towards the southwest, but thankfully trees will be able to move along with it. There's going to be a lag between the change in the bioclimatic distribution and the distribution of many of these species, and there will be relictual populations that will still persist outside of these core areas. It wasn't a bad model, we were fairly happy with it, but there were some problems. It wasn't adequately tested, and I used too many variables, particularly in the Maxent model. So we went on to refine that and try and make this sort of modelling a little bit more realistic. In this exercise, I looked at the Koomal and its response to fragmentation because, well, basically it's the great double whammy of climate change and fragmentation. So we're looking at how these things respond and react to different degrees of fragmentation. So I spent a year radio tracking these around the wilds of Margaret River. It was hard and I suffered a lot to do it. And we found out that, yeah, they can survive, 40% remnant vegetation cover if they're, despite lots of predators, they can persist quite well in there. They don't use dieback affected areas, which was something no one actually had noticed before. They're highly mobile, they can cross gaps of up to 1 kilometre as long as they can see the trees. And they use a patch matrix. They'll use a series of patches together, not just one. They'll use the whole landscape as much as they can. So we tried to put this information into a bioclimatic model. In this case, we started off just using the bioclimatic variables, but instead of the 19, we broke this down to a suite of 5 effective bioclimatic variables and got a very good sort of model. We also developed fragmentation variable, and I'm not going to bore you with the maths and study behind that, but we actually worked out a way to put the response to fragmentation into a model. And again, we've added a level of resolution. We've ended up with a much more effective model. We ran this situation through various climate scenarios and we averaged it out, and we took out 5 Phytophthora affected landscapes, and all of a sudden the future for just the common brushtail in the southwest is looking a lot more precarious. It is almost identical to the contractions we're going to see in the ringtail. So far, it's a much more improved model. It's adding resolution and it's adding real field observations. Having done all this work, Deepore approached me last year and said, we're having some problems with the northern quoll in the Pilbara. This is a species that was once common across the whole top end. It has now crashed, mostly as a response to cane toads. But the Pilbara, there's no cane toads there as yet. So they came to a group of us with this problem. And they said, OK, what we need to know with the mining problems out there, we need to know, are there going to be, a good potential distribution map? Where are they going to be? What are the high priority areas? What are going to be the impacts of climate change and what are going to be the impacts on cane toads? Went out there, had a look at what's been done, and there's 3 of the models that had already been done out there, and this is starting to look at how far some of these models lie. These are 3 supposedly similar models that give totally different responses. So we went back to square one on this one. And we started off with going through the literature and speaking to the people that know, and we looked at 53 different predictive variable data sets. 46% of these we tested as potential predictive variables. We were trying to get this number down to a manageable and realistic number of less than 10. We spent literally, and there were a group of us working on this, at least a month just looking at variables. And we went through a series of fairly heavy statistical tools and modelling practices to get it down to a suite of 9 predictive variables that we use for all our modelling from that point on. And we addressed all those problems we started looking at in our original Maxent model. But the biggest one we're looking at was sample bias. Although we had about 1,300 presences in the Pilbara, people have been going back and sampling the same areas again and again and again. So what it came down to is we only had a sample of about 340 different little dots for the whole Pilbara to try and work out a potential distribution model. We approached this by developing a sample bias layer. And to do this, we used all the sampling for critical weight range mammals that had been done in the Pilbara, saying, well, that's going to reflect the sampling effort for the whole area. And we developed a GIS layer out of that which we can incorporate in the Maxent model to compensate for that bias. And that was the model we ended up developing at the time. Statistically, it's very good. It gave us resolution, and more importantly, the people that work in those landscapes said, yeah, that's pretty much right. So being happy with that model, the first thing you do is you go out and you try and break it. And we tried something totally different to try and break this in a new modelling system there, and it's called Biomod 2 Ensemble Modelling. In this case, we took 5 different modelling tools, ran multiple runs of each one of those tools together, and combined the results. And these resulted in a series, and they were all combined by different areas, and we looked statistically, found the best model, which is that one there. It was a weighted ensemble model, weighted mean model, and we compared that to our original model. And it may look a bit messy, but those red areas are where the high priorities of everything match. We actually ended up, this model confirmed everything we'd been seeing in modelled in the field so far. We also ran some bioclimatic modelling, and this had to be done at a national scale with presences for the whole species, and it varies a little from the either. It lacks the resolution of our earlier model, but this is showing under the 8.5 scenario, 27, that's high emission 2070 scenario. The red and green are the original potential distribution, the yellow is the future distribution, and the green is actually those areas of potential distribution that remain valid for this species. So for this population, the green areas are apparently the safe bits. Then we went on to the cane toad. And this is where it all starts to go very wrong. We looked out there must have been about 30 models looking at the presence of these species across the whole south, well, around the whole country, and they vary enormously. As we're about to hear later, we found out later that there's a lot of things about modelling amphibians that change the rules, and this is getting back to the suitability of different species. So we had a look and found out it's a range-shifting species. So where they are, those presences don't reflect its capacity to actually exist. They still haven't fulfilled a potential distribution. There are cryptic variables, I was saying before, that apply to this species, and many amphibians don't apply to other things like moisture, enough rainfall during the summer months, even salinity and other little factors like that come into play. They hitchhike and they can use man-made water levels, so what should be a natural barrier to their movement across the landscape is in fact not a barrier. The Olympic Village phenomenon. As this species has been moving across a very harsh northern Australia, they've been evolving and changing to meet those. It's a situation where this harsh environment has rewarded the most adaptable. So the animals that are entering Western Australia now are very different to those that started the movement in Queensland. A lot of these models were put together under older and possibly less effective climate models and scenarios. So in response to this situation, we tried something a bit different. We went and developed a Boolean model, just a simple application of models. It works on the basis of the more boxes ticked, the higher the scores. We looked at the data sets that were out there. We developed a whole series of variables and parameters. That is, those variables that are listed on our left. The right, the values within those variables the species is known to exist. And we just overlaid those and just found out and compared these to the modelling techniques that had already been done out there and found out which are the best there. The result of this was this model here. The orange layer there is the 70% chance of invasion by cane toad across the Pilbara. The grey area underneath that is our northern quoll distribution. So currently, nearly all of the northern quoll distribution in the Pilbara is susceptible to cane toad invasion. However, as we saw before, there was a movement in the distribution of northern quoll. They were moving easterly. We ran both models again and compared them under the 8.5 2070 scenario. And we can see, actually, the cane toad distribution under climate change is contracting. It contracts towards the coast in a westerly direction. And the northern quoll population is moving towards the east. So we're finding under the climate change scenarios there's going to be some good news, there's divergence, and this gives us a chance to develop some actual real management actions that are going to be effective, and they're under development now. Now, last modelling exercise I'm going to discuss is a little closer to home for you guys, even though it's not mammals, it's the western ground parrot. It's down to 110 animals left in the wild, I was told a couple of weeks ago. I was speaking to some of our friends at Deepore and they were talking about, is climate change or could it be affecting them? So I ran a quick scoping exercise over a few weeks to have a look at how this might affect. Again, it was a simple exercise using Maxent in this case. We modelled these over the whole southwest because there were old presences from Perth and in the Fitzgerald to see how climate change may be affecting them. I had done no major research on this. As I said, it was just a quick off-the-cuff scoping exercise. If we're looking at changes in the southwest, across the southwest ecoregion, the top is our baseline historic distribution. To the bottom is the medium emission 2050 scenario. We can see there's already a fair change towards the southwest, towards the east and west. Medium emission 2070. High emission 2050. High emission 2070. We're looking at a major change in distribution. Put it at Fitzgerald. 2050 medium scenario, 2070 medium scenario, 2050 high scenario, 2070 high scenario. This was a desktop exercise. I went back to the people who are involved in working with this species and I said, well, I don't know, is this what you're seeing? We'd done in this, as I said, it was Maxent. Statistically, this was an extremely strong model and I'd ended up repeating this with several different climate models. And pretty much the same set of 7 variables, I think, came up for each time. And we found that, given that this is a scoping exercise undertaken as a desktop model, developed with a single tool and using bioclimatic variables alone, and any other caveat that anyone else can think of, we find modelling contractions and potential distribution comply very strongly with observed declines in the field. Models indicate severe high temperature events and decreases in summer rainfall are the major drivers. There may be other unidentified drivers at work, there almost certainly are. Responses to variables may be causal, indicative or coincidence, we don't know yet. Feral predators and other anthropogenic impacts are certainly exacerbating and magnifying climate change impacts. We took all this and we developed, again, an ongoing management program on how to incorporate species distribution modelling into the further management of this species and others that this shares the landscape with. So, having spent the last 5 years doing all this work and a fair bit more, I've developed a few take-home messages on species distribution modelling. Be very sceptical of your findings. Bad SDMs lie. They lie a lot. Be very aware of sample bias. Be aware of multi-collinearity. That is, keep those numbers of variables down to a minimum and keep them relevant. Try to break your every model. Test them to hell. Or someone else will come along and break them for you. Support and enhance desktop work with field studies. Desktop work by itself without field work is useless. Horses for courses, be adaptable and diverse in the modelling tools you use. The old term was, if the only tool you've got is a hammer, then every problem starts looking a lot like a nail. Not all species are equally suited to distribution modelling. And most importantly, SDMs inform experts. They are not they are not a substitute for knowledge or experience. They are there to enhance it. And when you've got all those boxes ticked, that's when you sit down at your computer and get to work. Thank you.